Hello students, welcome back. Now let's begin section 3, Independence. This topic is another continuation of section 4 of previous lesson, the multiplication rule. So that's where we're going to begin. A review on multiplication rule. The probability of A and B equals to the probability of B times the conditional probability A given B. In other words, B takes place and then under that condition, A takes place. B and then A. Now, can I switch the order? Yes, I can. I can start from A and the probability of A, and then under that condition, the conditional probability B given A. So in short, A first and then B. Previously, B first and then A. Either way, you're going to get the probability of A and B, the intersection. And the proof is rather simple. From the definition of the conditional probability, flip this denominator to the other side and that's it. So algebraically, it was really easy. And in terms of empirical understanding, well, we're going to go over some example problems, so stay tuned. But before that, let's talk about independence. Now, these happen in general, but there are some special cases where probability of A and B happens to be the same as just straight up multiplication. Probability of A times probability of B instead of going through conditional probabilities. If that happens, we say events A and B are independent. So, compare this with the first expression here. Please note that this straight up probability of A, which I just highlighted in red, must be the same as this conditional probability. Because the others are all the same. You see this probability of B, this one, which I just highlighted in blue, is repeated precisely here as well. And then as for the left-hand side, they're the same. So this red and that red must be the same. So this multiplication rule is actually equivalent to this red versus red. The probability of A equals to the probability of A given B. Now, if you compare this with the second expression, you can get the same conclusion here. I mean, probability of A is repeated, so red versus red, no problem there. Now let's focus upon this conditional probability, which I'm highlighting in blue. This versus the probability of B. They must be the same too, because all the others are same as well. And this can be rewritten like this. The probability of B equals to the conditional probability B given A. What happened to this space? Okay, there you go. Now, this blue condition and this red condition and the black condition, they're all the same. They're all equivalent. So, multiplication rule, the special case where the probability of A and B equals to the probability of A times probability of B versus the original probability and conditional probability of A are the same, or the same thing for B, they're all equivalent. It's easy to see algebraically. Yes, it's easy to see algebraically and prove those algebraically, but then again, what's it like empirically? Well, let's study that using these two examples. Similar situations. 3 balls will be selected from an urn that contains 5 red balls, 3 green balls, and 2 blue balls. But in example 3.3, without replacement. So select a red ball, and then the next red ball, and then the third blue ball, like that. Red, red, blue. Now how about 3.4? This time it's with replacement. So when I get red, red, blue, just like last time, it's going to be a red ball, and then put the ball back in, and then reshuffle, and then select the next ball, and that too is a red ball. Put it back in, reshuffle, and then select the third ball, and this time it's blue. So there's a subtle difference between one and the other. Now, how do the multiplication rule differ? This is a multiplication rule for example 3.3 without replacement. So we take the red ball, and that probability is 5/10 because there are 5 red balls out of total 10. Now in my second row, the probability is 4/9. Why? There are only 4 red balls out of total 9 because 1 red ball is out and it was not replaced in. And then the third probability here is 2/8 because there are 2 blue balls out of total 8. You see, these are conditional probabilities. Under the condition, the first was red, and this one, under the condition, first 2 were red. Now let's go to example problem 3.4. This one's a little bit different. Red, blue, but the first probability is 5/10 because there are 5 red balls out of total 10. And then in my second row, it stays at 5/10 because we replace the ball back in, reshuffle it, and then select. So still 5 red balls and total 10 balls to choose from. The third row, 2 out of 10 because basically no change took place. This is wrong. Yeah, okay, that's right. Sorry about that. 1 out of 20, not 1 out of 40. Sorry about that. All right. And then one way to visualize that is, no, never mind. One way to visualize that is through a tree diagram. So first row 5/10, that's straight up probability. And next, this is a conditional probability because this is affected by the previous draw. There are only 4 red balls to choose from out of total 9. And then this one is also a conditional probability. 2 blue balls to choose from out of total 8. Now if I go one more, say another red, then the probability will be, 3/7. And then the next, and then the next. We'll just have multiplication. Now, how about the second example down here? We can use this to visualize the situation. 5/10, and then this is with replacement. So second row is completely independent of the first row. The ball is back in, so there's no difference at all. So 5/10 again. And then 2/10. Again, there's no difference. For example, from here to going back to this blue, that's 2/10, the same over here. Because the balls are back in, so I still have total 10, and then 2 blue balls out of them. And then if I go another branch here, say another red, then it will be another 5/10, and multiply like those. So with replacement versus without replacement, that's a good way to visualize multiplication rule for general case conditional probabilities versus the multiplication rule for independent events. With replacement, we have independence. Without replacement, we have dependent cases, so we have to consider conditional probabilities. Either way, tree diagrams will help, and they go with multiplication rules. And there are some students sometimes get confused with independence and mutually exclusive. If A and B are mutually exclusive, that means there's no overlap. A and B is impossible, so the probability of A or B happens to be the sum of the probabilities. Independent is for A and B. In that case, we can multiply the probabilities. It turns out that if two events are mutually exclusive, they can never be independent, and vice versa. If two events are independent, then they cannot be mutually exclusive. Well, of course, the exception is one of the event is empty event. In that case, hey, what's the point? All right, that was for independence. And then we're going to talk about how to utilize this independence, and especially associated to binomial distribution, which will be a big deal in Module 5. But we're going to do that in a separate video. We have to change some topic rather significantly. So stay tuned. Let's meet again in Session 4.